All right, so let's get started. So this is our first lecture, and the focus of this lecture is to becoming familiar at a high level. What are the database systems, and what are they used for? What are their importance, and what role they really play, uh, not just in the industry but also in computer science and their broader impact. So that's what we're going to be kind of learning in this course. And today we're just going to focus on some of the key properties and fundamentals of database systems. And week after week, we're going to look and dwell into one of those components each time. So, and hope by the end of the quarter, we will develop that deeper understanding of a relational system in particular. So, what is a database? So that's a question. So you can just tell me, what do you think a database is, or what is it used for, and why even bother with having a database?
So I would say it's a system that is used to store data, um, right?
Yes, that's good. Yes, absolutely. That's what we're used for. But why have a database system? Why not just the application or the user handles the data? What's the benefit of actually creating a database software?
The book was saying that it's used to like manage resources in an efficient way, and I think there's like security benefits, and like if your database crashes, being able to come back.
Exactly. So again, so it's very important because when you deal with data, you have to make sure the data is secure. You have to make sure that if there's crash, the data can be recovered. And you also have to make sure that multiple users can access the data. And those are all important properties. But why not? Why not just the application that needs to access the data? Couldn't just the application implement those functionality? What would be the issue with that?
It cannot be shared by multiple applications.
It cannot. Yes, that's a really good point. Is that if I kind of embed my database inside my application, then it becomes much more harder to expose that to other application. Again, that functionality can be built, but then we're kind of going back to this routine. Is that now every single application needs to duplicate the same functionality of how do you manage the data, how do you query the data, how do you secure the data, and soon just the managing of the data is going to become much more complex than the actual application logic. And we're just reinventing the wheel every single time. So that's the point, that you realize, okay, so then the database can be a service or can be a software on its own, that I can actually pull it out of the database, out of the application, and make it as an independent software. And so make your application much simpler, as opposed to application dealing with even the maintenance of the data. It only focuses on the logic of the application. And so that's why, I mean, even in the back in the 60s or even 70s, many applications would actually uh, focus on or take on the task of managing the data. But then once the relational system or the databases become more commonplace, the application simply became more easier to handle, becomes much simpler, much lighter, because they offloaded all the management to the data. And in the same way, you have operating system. So the application doesn't need to manage the entire memory of the machine, or it doesn't need to manage all the devices. The operating system will handle that, and it provides an interface for the application to use the disk. It provides the application to use the memory. So again, it makes the application much more easier. So the general trend is, and this is not just limited to databases, is that if you see there is a common utility, or there's a common uh, uh, component keeps repeating itself across application, then in general you may ask, well, maybe this is something that can be extracted out, and I kind of build the software or build the service. Especially with the cloud, we really focus on also building services, not just software. So I can build standalone software that handle it. And the difference, I'm sure you're all kind of familiar with that, is that what is the difference between a regular database that I start up versus a service of a database. And the difference is that with the database, if I'm managing the database myself, I also need to figure out how do I install this software on a set of machines, how do I configure those machines, and I need to maintain that installation and then also apply the patches, the security updates, and all of that. Versus the service, I'm not even, so it's even taking the application even, or the development shop is much simpler. Before they had to deal with the data inside their application. Then they pushed all that functionality into a database. But now with the cloud, we don't even have to worry about managing or installing a database. I just use a database service on cloud, and the cloud provider even take care of that management part, the deployment part, the patching, and all the other tasks that is required. So again, the applications has development of the application has become much simpler over time, and that's a trend that is continues uh, in just in software industry as a whole. So that's the key notion or the key necessity of having relational system or databases in general. And in general, what we find is that it doesn't matter what industry you're in, or it doesn't matter really what application you're dealing with. If there's no data, it seems to be not much to do. I mean, every task that we do, when you kind of look at it and examine it closely, it relies on data. We get some input, that input is a data. And somehow we look at the past state, and based on the past state or the current state, again, as an input, we can decide what to do next or what action to be taken next. So applications essentially automate taking a set of actions, and those actions are not going to be just flipping a coin on arbitrary. It's going to be related, or it's going to be based on set of data. So data is at the center of every single application that is out there. I mean, I cannot imagine an application that doesn't require data. And if you can think of one, I think it would be interesting to share it. But any practical application needs to deal with data. And oftentimes, and especially in this day and age, as we tend to collect more and more data, sure, there's a major ethical and the privacy issue that needs its own consideration. But at the end, is also is a wealth of information in this data. So this database systems need to be able to scale to these large collection, and often of different forms. So it could be video, or it could be images, or it could be text, or it could be relational. So the modality of this data is also continue to increase. The variety and the volume of it continues to increase. And there are, when you also look at the data and you talk about, okay, I have this large volume of data, you need to be able to reason about the data, you need to be able to structure that data, you need to be able to model that data. And one thing that has become very useful, and that is one of the key cornerstone of relational model or relational database system, is that this notion of seeing the world, and we do this in programming languages as well, whether it's Java or any object-oriented programming language, we do have that notion as well. We have notion of objects or entities, and then we may have a notion of relationship. And the relationship is connecting entities together. For example, in student taking a course, so that is a relationship. And the relational model is very simple, yet extremely powerful, because it has been able to support applications in the last 40, 50 years. I mean, it was introduced by COD at IBM Research in the 1970s, and it's been 50 years that enterprise is relying on relational model. The backbone of our economy or just software is relying on the relational model. So it's a very simple abstraction. You have entities and relationship, and that's tend to be very powerful. in a very simple way and very intuitive way allows to model very complex relationship. And this is something toward the end of the course when we look at the query languages, because it's one thing to model, and then there's also another thing is that depending on the expressiveness of the model, you can also determine what kind of question that can be asked. So there is a relationship between the expressiveness of the model and also the expressiveness of the query language. They go hand in hand. So that's something we're going to turn our attention toward the end. And so again, the database itself is going to be packaged as a software, and that's the way it was in the 70s, in the 80s. But up around 2000 with the advancement or the adoption of the cloud, that has also changed. So it's not just the software packaging as a software, but now it comes as a service. Every cloud provider does provide a service, database as a service, like Amazon RDS or Google Firebase and Oracle and DB2, they all, or SQL Server, they all have their own service instantiation of their database system as well too. So it's another form that they're being delivered and used by applications and by customers. So that's kind of the general overview. Any question at this point? And now the question is maybe something more simpler is that, well, why not just I use files? I mean, I already have this nice abstraction and I can open up a file and write into a file. Why not just use files instead of relational databases? And in fact, I could say, well, I have operating system. Operating system gives me these abstractions of files. And so I can just use the operating system facility and write my data into files. So what would be the challenge in there?
One challenge could be the speed of looking up data within the file.
Exactly. So the operating system is not designed to provide high throughput changes to the files, because when you look at it, typically the usage of the file, it's maybe you open it, you're reading it, maybe you add something to it, but it's not designed. It was not the intention of opening of a file and then supporting the Amazon sales during the Black Friday. I mean, the file was not intended, was not designed. That's not the typical use case. That's not a typical by any means a use case of the file. So again, in terms of abstraction, you could say, well, you talked about relations or relational model. They could be implemented as files, but using files natively as just databases, it simply doesn't have all the functionality that we mentioned. It doesn't have the security, it doesn't have the recovery, it doesn't have, does have limited ability to provide multiple people accessing the file, but it's very coarse. Oftentimes, the way the operating system provides synchronization for the file is that only one person gets access to writing it. So if multiple people are wanting to access it, well, they kind of just be blocked. And they just have to wait in line till they get their turn. While inside a file, you could have thousands and thousands of records. And those people who are being serialized to access the file, they may be touching different records in that file or different segments of that file. So technically, they could have all proceeded at the same time, modifying it. But again, those abstractions are not within a file. But when we look at files, I mean, the notion of the sort of the physical abstraction of the file is actually used in databases as well. So at the low level, you can think of as a file as a way of storing the data. And the database itself may have its own definition and constructs, but it may also use the database, the operating system. But that's at much lower level granularity. We're talking about low level kernel level accesses. And again, files are just, they don't have any query interface. They don't allow us, you can just basically read a bunch of characters, or you can seek into the file, go to the beginning, go to the end, or go somewhere within the file And that's the functionality. It doesn't allow you to impose a complex query and then have an optimizer that figure out what is the best way of answering that query. Again, none of that exists in the file. And as mentioned, is that you're not going to be able to do the synchronization. You could do a synchronization at a very high level, so kind of getting a lock on the whole file, saying that I'm going to get a write access to this file and just lock everybody out. Sure, that will work. It's not going to scale, and it won't be a solution. It wouldn't be a real solution. Sure, it will satisfy the consistency, it will satisfy the correctness, but it will not really be practical in any sense. And again, the crash recovery. That's something that it's not really provided by files. So typically when you make changes to the file, it is possible that even there could be even possibilities that when you're saving things to the file, the operating system, there might be a lag on the operating system to actually the information that is saved in memory to physically push it into the persistent storage. And so there could be a potential window that you thought something was being changed, but it hasn't been pushed to the persistent. So if something crashes, whatever was in main memory, because main memory is volatile, then you will lose it. So again, that would be another main challenge with crash recovery. Again, file don't support it. They're not designed for that. And again, that was something that you've already mentioned as well with regards to just the need of the database is the security. One other thing in addition to security is about making sure that you stop malicious access, or you don't, not just anyone can look at the data, but in addition to have just that general security, you want to also have access control. And the access control, it's a form of a security, but it's more fine control. Is that saying that Alice has access to the database, but Alice can only look at selective set of records. It can't just look at everything, but Alice is authorized to access the database. So now the access control allows at a fine granularity who can access what. So again, that's something that the file doesn't provide, and the simple file abstraction simply just not there. Any question? So again, why the database? And some of these, we're gonna kind of keep repeating it, and every time kind of go a little bit more depth in it. So we talked about efficient access. So that's important. That efficient access is important because we want to be able to potentially scale to millions of transactions per second, meaning I want to be able to do millions of sales per second, or maybe I want to do millions of changes to the data per second. And I just don't want to do it from a single user. I also want to be able to do it from many users. So the idea of database is this shared resource or this shared data that can be modified by more than one user. But also there is that data independence. And we're going to talk about the data independence, which is a really important topic, and it comes in two forms, logical and physical independence. And that's kind of, at a nutshell, is that how I'm going to use the data as an application should not be dependent on how the data is actually being stored and retrieved. From the application logic, I care about maintaining the list of students and the list of courses and knowing which student is taking what course. Now, how do you manage this at a low level, whether you want to store them in a file, whether you want to store everything in one file, or you want to store everything in different file, or you want to put each record in one file, doesn't matter. As long as that abstraction can be provided to the application, that's the only thing that it matters. So that's the independence. And that's, again, that's one of the key success of relational system, which I'm going to talk about a little bit more. And the other point, again, we've already covered, is that if you have this efficient way of managing and accessing the data, and you don't have to do it as part of the application, so the application runtime or the application development is going to be reduced substantially. In fact, a modern database system, and by modern means those database systems that have been around for many years, like DB2 or SQL Server or Oracle, these real commercial database system, not just something that was put together as, like, let's say, NoSQL system within few months. These systems could have millions and millions of lines of code. So they're a really complex system. Most applications by no means have that level of complexity. So it's simply just not economically feasible in any form or shape to be able to reach that complexity of that the relational system has within the application. It's not economical from development time. It's not economical from the time and effort needed to implement that functionality. And more frankly, it is much easier to find engineers and developers who can build application logic than it is to build scalable database system or operating system. So even from the human resource, the talent required to deal with the complexity of the relational system or an operating system is far more than the complexity of dealing with the application. So it's just much more difficult building these building systems as opposed to building just application. And the other thing is, again, we're mentioning it, but let's take it one step further, is when we talk about the security is also the integrity of the data. So not only we want to make sure that there are no unauthorized access to the data and no unauthenticated access to the data. I mean, the user has the authentication to access and they are authorized, meaning they actually have the permission to access that particular record. But also you want to make sure the change, even if the user passes through all those security measures, we also want to have a model of the data and say, what is the semantic of the data, or what the correctness of the data is. So we do think of the data as entity and relation, at least in the relational model, very simple, basic model entities and relationship among the entities. But also we have some integrity constraint. For example, we may say, again, it's used in practice, is that you can't sell a book that you don't have. If your inventory of a book is already zero, you can't be selling more of that book to customers. Or if your bank account has a balance of zero, well, you can't give $100 or you can't purchase any more items. So that seems to be a very simple constraint, but that's something, again, wasn't easy to employ or express in files, but that's something the database provides. So it allows to define a set of integrity constraints of different level of complexity that says what defines a correct state of my data, or what defines a consistent state of my data. So that means any changes made to the data must satisfy these constraints. So for example, if I want to do an account transfer, there should be sufficient fund before that transfer can take place. And again, the database allows us to provide those constraints, and then it ensures that those constraints are in fact satisfied. And again, so administration, so that's something that's an interesting point. If you remember, I mentioned is that traditionally when you got your IBM DB2 or your Oracle, you had to decide of how to configure it, install it on machine, and you have to administrate it, and that is a major cost. But with the adoption of the cloud, now Amazon or Microsoft Azure or Google Cloud will do a lot of that administration work, and so they sell this database as a software, as a service, as opposed to be as a software. So again, part of that administration will goes into that sort of the cloud side of things. But even on top of that, there's additional administration involved, and that's in terms of how do I figure out what is the best set of relations and entities that I need to create, but more importantly, how much memory I need to assign, or how much CPU I need to assign, or even more dependent on the application, what kind of indexes or what kind of views I need to create in order to speed up my query evaluation. So the assignment of the memory and the CPU and the number of machines, that's something that the cloud provider could potentially handle. But deciding on what kind of indexes you need to add in order to speed up your query, well, in future, I think they probably could get to that point, but yet not yet. But again, so there are some administration even one needs to handle, even if you're using it as a service. But the notion of the administration or the facility of the database to provide the administration, whether it's a cloud provider is using it or the application developer using it, still remains as an important component of the database itself. And again, this is something we've touched about. It's crucial: concurrent access and recovery. So I have shared resources. I want to be able to allow multiple users accessing it, and I want to make sure those access are correct. I can reason about the correctness of those accesses, and more importantly, if something goes wrong, I should be able to recover into a consistent state, and any promise that I have made, any transaction that I have committed, any book that I have sold, or any successful account transfer that I have done, it should be able to recover those commitments. So that's important from the crash recovery. Anything that was committed, anything that the database makes a commitment to, needs to be able to be recovered after the crash. And anything that was partially in process, but it never reached that commitment state, one way is to just simply drop them and forget about it and have the user to submit those requests once more. So that's a traditional way of handling it. Of course, one may find a more clever way of saying, okay, I'm going to keep my partial things that they were happening partially and try to finish them up. So that could potentially be another way of doing it, but most database systems don't do that. So any question? Jim, are you asking a question? I see you unmuted yourself, but I can't hear you. I guess your mic is not working. Anybody else? Okay. So now in terms of why studying the databases, or maybe you could even say why, again, it's another questions of repeating the same thing in terms of conceptually why use of the database from the application perspective, is that you want to be able to shift from computation to information. And that's what basically means, is that as opposed to be able to worry about how the actual data is stored or how the computation is performed, from the user perspective, I want to look at my information. I need access, a uniform access to my information. I don't need to really be bothered with how that information is being stored. So from the application, from that business need, so then whatever the mission of that company or that enterprise is, it's not really about, most likely they're not about how to manage data. It's about how do you provide a better customer service to their customer, whatever their industry may be. So, and they do care about the information about their customer. They do care about how the information of the customers are secured and accessed and so forth, but they don't really care about the lower details of that. So again, so that's the database will come into the play of managing all that computation necessary in order to provide that abstraction of giving that view to the applications. And especially in the last 10, 20 years, we've seen a real increase. And so there was this hot trend in, I guess, in early 2000 or late 2000, between, I guess, 2005 to 2015, somewhere around that range. The notion of big data became really hot topic, both in research and in industry. And the notion of the big data, it consists of talking about the volume of the data, the sort of the sheer volume, especially with these web company like Google and Facebook and these social networks or YouTube with all the media and all the videos that they have, talking about petabytes, no longer just gigabytes or terabytes. I mean, some of these entities have petabytes data. So the volume has been increasing. The variety or the diversity has been increasing as well. So in your social network, it's not just that you're sending messages to your friends, you're also sending videos and photos and other form of communication. And some of them now, you can, there is audio and video involved, not just of old recorded, but like having an interactive video and such as Zoom, for example. So that's another type of data in terms of the diversity. And there's also a notion of a velocity of the data, and that's how fast the data is moving in terms of its creation or in terms of its ingest. For example, how many users are posting new tweets per second or per minute, and there could be millions and hundreds of thousands. And if there is a big event or there is a disaster, then all of a sudden there is a surge in the number of new data item that is being created. So the volume is another important. There's another dimension is the veracity. So we talk about 4Vs: volume, velocity, variety, and veracity. And that one is about the certainty of the data. And as we just, let's take Twitter, for example, not every information that is posted on the Twitter is accurate and correct. Or in general, if you, for example, have sensor data that you're collecting measurements, well, not every sensor is going to work correctly depending on its weather condition, its battery condition, or so many other factors. So the uncertainty of the data also becomes an important element that needs to be taken care of, especially when you query the data or when you ask questions about the data. And of course, these uncertainty also arises in machine learning models. So if you're running your deep learning and you have this statistical model that you have developed, well, the answer that they provide they're kind of probabilistic or approximate. So there must be a principled way of dealing with probabilistic, the data that are by nature probabilistic. So how do I query that data, and how do I make a decision? Because at the end of the day, if the goal is to make a decision, and that decision could have many consequences, you want to be able to have certainty of that decision based on the input data. So again, that's another important element. And DBMS, as I mentioned earlier as well, given the data is just so central to everything that we do, it does span the entire field of computer science. And you could think of, perhaps one way also think about operating database is an data-oriented operating system. And it's an operating system where at the center of it is the data, as opposed to be a process. So operating system, we could say, is a process-oriented architecture or infrastructure, versus databases is a data-oriented architecture. And within a database, again, it has its own, it essentially is a form of an operating system. It has language, there's theory, and there is expressiveness of what can be stored, expressiveness in terms of what kind of question can be posed or can be answered. And it does have many other elements that does, again, cross many of the field in computer science. So it's been a very exciting area of research, and it's been a very fruitful and a practical piece of software that has been developed and continue to be expanded and developed in today's time. One of the new exciting things coming out of databases is, I'm sure some of you have heard, is the blockchain. And the blockchain is, the way I kind of see it, as a resilient and a secure, even more secure databases. And it allows that the decentralization and democratic way of managing the data. So traditional databases are often have that centralization point, but with blockchain is really decentralization and democratization of every aspect of that process, everything that we talk about in a decentralized way. And for example, my research group, I mean, this has been our focus. I mean, I've been looking and studying databases for the past 15 years, but in the last 3-4 years, the focus has been on blockchain. And so we have our own platform, ResilientDB, and I do offer courses on blockchain. So last quarter, we had 2 courses, 189 and also the 265. So throughout this course, we're going to try to find at least one session to talk about the blockchain and all the exciting development that is happening in that arena. But I think we'll kind of need to wait for that to happen. But of course, anytime you have questions, I would be more than happy to answer that. So any question on this slide before I move on to the next? Okay, so we've already alluded to the relational model and what the data model is, and it's a topic, it's a phrase that we're going to hear it quite often in databases. You can think of as essentially a collection of concepts that helps us to define and think about and reason about the data. And the schema is the description of that model. For example, in our relational model, the main concept is that we have entities and relations, and you can think of relations as just a simple table with rows and columns. You can look at your spreadsheet, that could be your table, and that's your relation. And the schema is now defines what of each columns mean. So if you have a table, the first column could be age, the second column could be name, and then the third one could be social security, or it's just a description. So one is in terms of what that model is we can think of it as relations, and the relation is basically rows and columns. One is now the schema of that relation, which gives you additional information, describes the field, the type of the data in that field, the size of that field, whether that field can be null or it cannot be null, whether that field is automatically generated or if it's user provided, and that list kind of goes on. So it really defines all the details of that relation. And then we could create this. So we have our concept. So we talk about entities and relationships about this entity. So that could form our conceptual model. And on that conceptual model, we have our physical schema, and then we have we have our physical schema, and then we have our conceptual schema, and then on the conceptual schema, we can define further views. For example, I could say I have my physical schema is how does the actual data is. We can think of how my data is actually stored in terms of files, for example, on the disk. My conceptual schema is that I have a student relationship, and I have a student entity, I have course entity, and I have student taking a course relation. And then on top of that, I could create views. So for example, on the student table, I could have multiple views. I could have computer science students, I could have biology students, for example. So that could be different view on the same student table. So that allows you to manage that data and reason about that data. And the views also could be one way of providing access. So for example, if I have a user that I want that user only access the computer science students, then instead of giving access to all of the students as my table, give access to the student table, my student relation, I could just give access to that view of computer science student, which is a subset. And also the word relations and tables are often used interchangeably, which I did it intentionally in the last few minutes as well. So tables and relation it means really the same thing. And the basic of it, to simplify things as much as possible, all it means is the tables of rows and columns. Think of it as a spreadsheet, and think of it as also usually what you do on top of your spreadsheet, you're going to have a header line. Say this is the name, this is a, you define what each column is. Think of that first row as your schema, and your table, well, it is your table, so that's your relation. And you can also in your spreadsheet define what the format of every column is. So that's considered as part of your schema. And I think that's the simplest way I can describe it. And I really think it's just as simple as that as well too. And the notion and the entity itself is going to have a table, a bunch of columns, and it has a schema. And if I have two different entities, then I could relate those entities by putting that in, for example, take the ID of the student, take the ID of the course, and put it into a third table. And that third table, conceptually, I can call it, it's a relation table because it relates an entity of the student to an entity of the course. For example, Nicole as a student, and she has an ID of 5, and the course 165 has an ID of 10. And in that third table, I say Nicole ID 5 is associated to ID 10, meaning Nicole is taking 165A. So entity itself, both relation entity at the end of the day is just a table, and the table has a schema, defines what those columns are, and I can define views on top of my tables, and that view may expose a subset of columns, or it may expose a subset of rows. And that could be in the definition of the view. And views allows me to kind of look at a finer scope of a larger table. And it may be used as a simpler way of querying the data. Kind of, if a column has 1,000, if a table has 1,000 columns, to avoid overwhelming the user, I can just create a view of 5 columns that are relevant to that user, and the user can just focus on those 5 columns. Or maybe because of the security reason, I only want the user to look at these 5 columns, so then I can create a view. So that's one reason of why we would create views. Any question?
Are the views like generated through the syntax of the querying language that you make for the database?
Yes, excellent question. Yes, so interestingly, so the query language for most databases, at least for the classic databases, is SQL or SQL, and and also you express the definition of the view is also in a SQL-like language as well too. And the view could actually be a SQL statement. Kind of, the view is get everything from the table, where, for example, the department of the student is computer science, essentially extracting a subset of the students who are computer science major. But the other interesting question about the view is that the view could be just a logical mapping, or it could be just a query, meaning that the view data itself is not, the data is not copied into the view. The view is just a definition. So if I want to access, so I want to see what's inside the view, I look at the definition of the view, and I use that definition to extract a row into my student table. So the view is not materialized. But there's another way of considering a view, is that the view itself, it has its own storage. So it is materialized. So the data that is in the student table is replicated partially in the view. And there's pros and cons to both approaches. So if the view is not materialized, then I don't have to worry about the data. Every time somebody asks me, every time somebody poses a query on the view, I can translate that and map that to a query on the student table. Everything is good. But now, if my view is something else, so for example, if I define a view on my student table that keep a tally of the number of students in every major. So computer science major has 2,500 students, chemistry has 500, management has 3,000, and so forth. So now my view is just the number of students per department or per major. So so let me ask you that question. So, and that's a valid view, but what would be the benefit of this view? As opposed to I sort of define that view as a query over the student table. And I know how to do that. For example, I say, give me all the students of computer science major and then tell me how many they are. So I can always, I know how to pose that. So what would be the benefit of, first of all, let me just ask that, is it clear between materialized and non-materialized view? I guess that's the first question. Is that clear? And if so, then let's look at, I can't read the chat, so you need to speak up. As I mentioned, my cursor have stopped working as soon as I go to the PowerPoint mode.
I think people are just answering each other's questions in the chat.
Oh, okay. All right. Thank you for clarification, because I see the numbers going up and I have no way of hitting that.
So I have one question for clarification, if that's okay.
Of course.
So the view isn't the data available to be queried, it's the data returned from a query. Is that right?
So view conceptually is slicing the data of the original data, and that slicing could be a subset of rows or a subset of columns or both. So the view could be just a definition. Is that the definition of the view is, if I need to access the student table, I can say, okay, give me all the computer science major students. So I can write a query and get that data. Or I could define a view, and the definition of that view is computer science student, and the actual under the hood, what that view is just a query saying, give me all the students who have a major of computer science. So now if I'm a user and touching the computer science view, then I don't have to worry about that. I don't care if I'm not, as far as I see, I only deal with computer science student. I don't need to filter anything out. So it simplifies my access. So it simplifies the way I'm going to access the data, because as far as I'm concerned, I have a view of only computer science students. So as far as a user, I don't have to be worrying about the management students, or I don't have to worry about filtering out any other department. I can only ask questions about the computer science student. Versus if I wanted to go to the original student table, I can still ask the question about the computer science student, but first I have to filter out the non-computer science student. And within that, I need to ask my question. So that expressing that question is just going to be more harder, because there's more step to it. First, filtering out all the computer science, non-computer science, then answering the question on that. So the view kind of gives that abstraction. You can look at a subset of the data. You could look at a subset of rows, or you could look at a subset of columns. For example, maybe you want to create a limited view of students, in a sense that you don't want to show their social security. You just want to show their name and age, for example. And there's addresses, there's social security, you're going to hide that. So you create a view calling it limited student information. And that limited information could be just two columns, name and age. And you kind of hide all the other columns from that view. So that's the notion of having a view. And just the name is, if you take the name, It's a view of the data. It's a different look at it. The data is, imagine, look at your table. That's my data, and depends, and I can just take my hands and sort of look inside my hand. And so, of course, when I look at through my hand, I don't see the entire table. I only see a portion of it. My view is limited to the diameter of the diameter of that circle that I'm forming with my hand, and that's just a view. It's just one look, one perspective of the data that is defined.
So then to your question, you just want the database management system to handle as much of that data parsing as possible, right? Because as a user, you only care very specifically, I guess oftentimes about a smaller portion of that data that you're trying to pull. So that's what the system's designed to do, right? So why do it on your end?
Yes. So now, that's again, that's an excellent question. So now, as a database system, so I'm a school administrator, okay? And so I know I'm going to have students, and I know I'm going to have courses. So as a school, at the level of, let's say, at the dean level, just making that up. At the dean level, I'm having students, and I know I have courses at UC Davis. So I create a student table, and I create a course. But also there is department. So there's a department head in computer science, and I don't want the computer science department to know information about every single student or every single course. So I create a view on my student, which is just exposes the computer science student, and I create a view on my courses, which only exposes the computer science view, computer science courses. So I give that to the computer science department, and I can do that for the biology department, for the chemical engineering department. So the data, so still in the database, I have student and table, and inside the database, I can now create a view and expose that view to different users. So all of this is still under the hood of the database. The database provides both the definition, allowing me to create my logical schema, student and table, student and courses, but it also allows me to create these views to be able to support different kind of application and be able to support different kind of users. So it's part of sort of managing who get to access what, and also simplifying that data that is being exposed to different user to not overwhelm them. Because again, I could have thousands of columns in one table, and if this user only cares about 2 or 3 columns, why would I give it 1,000 columns? And so why would I overwhelm them if they only need access to a much smaller slice of that data? So again, that's another reason to create that view. Does that answer your question? Okay, so any other questions? In the notion of the view, I think is very interesting because it's just an important concept. So any other question? And now, now the next question becomes the materialized versus non-materialized view. So far what we talked about is a non-materialized view, because the definition of the view was just simply filtering out a subset of the data. So I had a student table, and then my view was computer science student. And the computer science student, all it did, just filter out non-computer science student. So it was just a filtering. It was a query that just did filtering of rows. Yes. So it wasn't materialized. But I could also envision a view that is materialized. And that could be, I create a view is to count. So I would say, I can maybe call it student per major aggregate, or to essentially know how many students are in each major. And so I create this view that for each major, it counts the number of students. So computer science, as I said, has 2,500 students. The management has 3,000, and chemistry has 500, for example. So that information is coming from my student table, but I also remember those values. I kind of store those values in my view. It's not, my view is no longer just a definition of how to retrieve the data from the student table, but the data that is retrieved, it's also being stored. So that becomes a materialized view. The data of that view is also stored redundantly. I can always go to my student table and recompute it, but then the view also may materialize those answers, so materialize that data. So now the question is, why would that be beneficial? What would be the pros and cons of that approach?
It's faster for materialized data.
Yes, faster, but for what purpose?
Like, you don't need to count the size of the number of students every time someone asks about the size.
Exactly. So it is fat because, and so now, as you just precisely said, the materialized view, it was a computation. So that computation is stored. Now, if I want to ask again, how many computer science students are there or how many chemical students are there, I don't have to redo it every single time. And if I have thousands of students, then that's a pretty hefty computation. So it really provides that saving. So materialized view is always important for speeding up the query. And now think of a bit larger, if I'm running these very complex reporting or warehousing type of queries that could be pages and pages long, and they could be aggregating in so many different columns, having this materialized view, it's really going to help us really speed up those queries. So they are really powerful, but what's the challenge now with this materialized view?
I think like if you have to update the data very heavily, or you have like a very rate heavy payload, then you have to update that materialized view every time.
Exactly. So that's a critical problem, is that, and this is what we're going to see through the database theory and system. We always going to hit trade-off. We're never going to have optimal solution in anything we do, because we always going to have conflicting goals. And oftentimes they come to read and write. The notion of making things right friendly is often different from write friendly. Read, for example, perfect example here, I can have the materialized view, so I don't have to recompute. But as we just mentioned, if now I have do a lot of updates, I need to write, I now have to update all these materialized views. So before I only needed to update the student table, now I have to update every single view that is defined on students. So it becomes much more expensive. And traditionally, the databases have kind of said, okay, I'm going to build an engine that really optimizes the read queries, and I'm going to build a different engine that is really optimizes the write query. And what we're going to look at in this course as a project is the L store, which is how do I create a new architecture that allows me to do both read and write efficiently. Or in other words, I'm not going to sacrifice the write performance, but I can gain the read performance of potentially 100x of certain techniques that we're going to look at that it provides. So a nice compromise of doing an acceptable write, but doing really fast read. So and that's where the whole the course actually lies. So the materialized view, it's an important topic. And in fact, some would believe, or it's an interesting observation, many research problems across the board, it will reduce to the materialized view problem. And it's fascinating. So many different research problems, so many different theoretical questions, always reduces to materialized view problem. And in fact, the materialized view problem in general is not only expensive, as was mentioned, but it's an undecidable problem. So it's not always actually, it's not even possible to maintain. So we talk about materialized view maintenance, is that automatically be able to maintain and update my materialized view, and that process becomes not even computable at times. So there are cases that's not even, so it's an undecidable problem in a general case. So it's a difficult problem too, not just expensive, but it's also difficult. It's in fact, in general cases, not even tractable. But that's becomes a very interesting problem. indexes that we're going to talk, and you all have seen B trees or hash tables, and you all have familiarity with indexes. Indexes is nothing but a materialized view. So because it's a different, it's a view on the same data, but it's structured in such a way that allows you to have fast access. So it is a materialized view. And so that's an interesting, I guess, connection that one can also make. But that's the importance of it is wide abstract. Okay, actually, any questions before I move on? So again, conceptual schema, we could have students, we could have courses, we could have enrolled, kind of covered that. And the relations, these student, courses, and enrolled. So technically, students and courses are entity. The enrolled table, which I gave an example already, for example, Nicole taking 165 or Jim's taking 165, that could be a relation. But relation is nothing but just another table. And relations are often stored as just unordered files. So at the basic level, the database could use the notion, does use the notion of files. And the files are unordered in the sense that when you add records to the table, they're just simply appending it, could be just appending it to the end of the file. And what is file? File is a set of pages. And pages are just a contiguous block of data. So it could be 200 and it could be a 4 kilobytes or 32 kilobyte block. So a file will consist of many blocks or many pages. And so that's the operating system abstraction. So you could have a 4K page or you could have a 32K page. And a table is basically an ordered file, unordered files. And files is a set of pages that are chained together in various form or shape. And then the record could just be inserted on just in an append-only fashion, for example. And they are not often stored in any particular order. Of course, there's many exceptions and optimization and design to that. And we're going to look at all of that. So we're going to look at all of this in your project, and you will especially going to do work on persistent and storing it on disk in your second milestone. First milestone is all going to be main memory. Second milestone, we're going to look at disk. And then there's also index structure, as I mentioned, a materialized view, and you often want to maybe put a index on your primary key, and so that allows us a fast access to the key of the relation. So I can quickly find, given an ID of the student or even given the name of the student, assuming the name, I guess, is unique, I could quickly find the record of that student without the need of going and checking every single row in the table. And especially these are all unordered. They could be, and a table is a file, and a file is a set of pages, and the pages could be spread across your disk. It's not even pages physically when they're put on disk, they're not necessarily put next to each other. So if the operating system managing your files and the database is not managing the file, then they could be placed in any location. So that's going to be expensive. Of course, advanced databases will do all the low-level management themselves in order to make sure the placement of where the pages goes. So they do manage the page allocation both at the memory level and the disk level. And then we could have view, and then again we talked about this view is just a subset of a field on top of our course, on top of our tables, and it could also be a subset of records, subset of rows, subset of columns. So overall, looking at a database component, basic concept, we have our storage on the bottom, we will have some indexes, which are nothing but materialized view. We have our log, where kind of anything that we do, we keep a journal. So every task, every changes to the storage, we keep track of it in a journal or in a log. Why do we keep a journal? So that we can recover. Because if we are very careful in our writing our journal or in our writing our log, then we can always restore to a particular point in our journal. So as long as the journal is there, so the recovery of databases relies on that log. And then there is also, as we said, we're going to have multiple, we're going to have allowing multiple users to access the data. So in order to have concurrent access to the data, well, naturally we need concurrency control. And the concurrent access, well, we will have many execution threads or the worker threads that allows us to access the data and the storage. So perhaps this is a good point to stop, and we'll kind of continue. And so what we're gonna do, so we're gonna, in terms of the milestone, and this first milestone is to have single-threaded execution. So we have these execution thread. It's going to be just one of them. We're going to have an index, and our storage is just going to be in main memory. So that's our milestone one. So it's really, we're going to look at this picture and really get a hands-on experience. So milestone one, we're going to have a single thread. We're going to have an index. We're going to have our storage. And then in-memory storage. Second milestone, we're going to add disk to it. We're going to add our log. And on the third milestone, we're going to add that top box of concurrency control. So, and then this will be our course in one nutshell. So we're going to look at all of those pieces, and they're going to build all those pieces together. In 3 milestones. Any questions?
Yeah, can you describe the index component a little bit more?
Sure, we're going to spend a lot of time on the indexing, but just general, like you could have a hash table, or you could have a B tree. For example, if you want to, so you have a student table, you can hash on the name. So given a student name, given Alex, then I can quickly find all the details about the Alex. One way I can always go look at every single record in the database to find where Alex is and then retrieve all its information. Or I could go to the index. The index tells me Alex is on this file, and it's on the 20th page of this file, and it is the 5th entry on the 20th page of this file. So I can just jump to that position at a high level, and then I could just quickly retrieve it. Otherwise, there could be thousands and thousands of pages that I had to examine one by one. So I could be spending hours reading through every single file, every single record to find the Alex, as opposed to allow me that jump. I go exactly in one, almost like a constant lookup speed to records for Alex.
I have a question about the materialized view, if that's all right.
Of course.
So I guess I'm just curious, like say, is the database management system kind of, I guess, aware of what type of application is querying it? And so it will know, like, I guess, what kind of API endpoints there are and preload those, like it's constantly just refreshing those. So when that query does happen, it's just spitting that data out quickly. And so it's just constantly churning those based on the endpoints of the application that is, I guess, querying it.
Yeah, so again, that's another excellent question. So generally, you would create your tables, you could create your schema. Like, for example, in our case, we create our student table, we create our enroll table, and we create our courses. We may want to create some views we may not, but just I think the question just as valid even if we had no views. Views, the database is not going to create it for us. We, as an application administrator or database administrator, will figure out, well, we also, our student table is too overwhelming or has too many records. I don't want to expose that to everybody, so I create a view, and so I define these views. So that's, again, as part of the database provides you a facility to create tables and to create your schema. It also gives you the facility to create that views. So that's something that is on the user side to create. But now your question still remains, that's an important question, is that if my data, it doesn't, so actually let me just answer a simpler one. So the database could kind of look at the type of workload, the type of queries being run, and notices that it's really likelihood that the access pattern or the way the data is being accessed is that we keep want to look up a particular student. So then the system may suggest that why not create an index on the student name to improve these execution. So there are facilities like Index Advisor in these databases that they observe you can give it a set of workload, you can give it a workload, you can give it a set of data, and it will suggest what indexes needs to be created to improve the execution. So that's one level when it comes to indexes. So kind of observe the access, how the data is being accessed, to suggest what indexes to create. And these are usually the space of possible combination of indexes to include, given all potentially hundreds of tables, it's exponential. So it's not an easy problem. And so there's been many research, it's an ongoing research for decades of how to build Index Advisor. But there's also another thing that is also happening, is that even if I have all my indexes already, I have optimal set of indices, I still, and also if the case that my data doesn't, for example, fit entirely in the memory, I have petabytes of data, but I have gigabytes of memory, then I have to constantly bring set of data item to memory, because that's the only way that the processor can read the data. Processor cannot read it directly from this, brings it to memory, and from memory it goes to processor and then to the user. So now the question is, which data items I need to bring memory, and when I need to clear up the memory to bring a new page, what data to evict. Again, by looking at the pattern of the access, I can decide which pages are more likely to be accessed in the near future, and what pages are least likely to be accessed in the near future. So if I need to make a decision of what to keep in memory or what to drop, that becomes, again, by observing what's happening in the system. Again, this is something the operating system wouldn't be able to do, but this is something that precisely the database system will look at. So that becomes part of, for example, the buffer pool policy. And there is also other ways of, there's many other ways of kind of, again, it's also important to, even if I have, if I know what data I need to access, can I, for example, prefetch that data? If I know within the next 5 minutes, I'm going to access certain data, if I can forecast or I can guess that before even the user asks for it, I can bring it in. Or if the user needs to access a set of data, instead of just randomly going from one page to another, of doing a random access, if I have better understanding what needs to be accessed, maybe I can transform that random access into a sequential access. So look at the data in a sequential way. That will improve the performance both of the disk and even the performance of the memory. So again, all of those now becomes part of the query evaluation, is that how do I optimize accesses? So access control or access, not access control, access, actually they call it access control. Access control uses in both ways. So the access control, how do I, in what ways I access the data, in what pattern to optimize the pattern in which I access the data. And often you want to do it a sequential access. It becomes an essential optimization that is part of the query evaluation. And so constantly you want to try to optimize that. And there's a flow of the data. Data is in this, comes to main memory, then goes to the processor cache, and that entire pipeline needs to be optimized. And we're going to look at many of that in the coming weeks.
Is that something like including like a machine learning model or something to predict what the data is going to come from?
Yeah, so that's a very exciting new area of research right now, is to create machine learning model to be able to predict exactly what you said. So that's an active area of research. It has been a little bit challenging. There hasn't been a lot of practical solution yet, but I think definitely that's something very exciting. I think we will, so in fact, they are looking at machine learning model to be able to optimize and auto-tune every level of the database. So that's, I think, something to come. If you look at traditional system, DB2, Oracle, SQL Server, they don't really have an AI tuning model yet. So nothing has been shipped. Even the index advisor has been difficult. At least traditional index advisor has been difficult, because by the time usually the index advisor decide what the user needs, what queries are more common, typically that means the query have been issued those the users have issued those queries, which means the user realize, wow, this is going to take forever to run that query. And oftentimes what happens in practice, they said, this is a too complex query, they're not going to run it ever again. It's actually changed the application. It has an effect on the on what the user end up doing. So by the time index advisor has caught up to the workload, usually the user had made the conclusion, probably this is something that cannot be done. So its adoption still very useful, but has its limitation. Now maybe machine learning model can do a better job, and I definitely think there's potential there, but I think it's an open area of research at the moment. Any other question? So I think this is a good slide to end, and we're going to look at the concurrency, sort of a very high level of concurrency and transaction, and the remainder of the slides. But this really gives us what are you going to be built for your project. So we're going to look at all of these components, and we're going to build that sort of this database system, in particular LStore, with its unique storage architecture. All right. So if no further questions, then have a wonderful day, everybody.